In this video, we'll consider the writing of the nucleophilic substitution reaction mechanism. So here I give two examples. We'll start with the top example. The idea here is we need to figure out which particular mechanism is going to occur. In a nucleophilic substitution reaction, there's always the electrophile and there's the nucleophile. Your electrophile will be that molecule that is attached to the leaving group. The leaving group will be a halogen. So I hope you can see that your electrophile is this fellow right here with the bromide leaving group. Now, in order to decide which mechanism is going to occur, one of the first things that you should do is look at the alpha carbon and decide if it's primary, secondary, or tertiary. As we have seen, if it's a primary alkyl halide, then we know for sure that the reaction will occur Sn2. It occurs Sn2 because there's plenty of room for the nucleophile to attack in one step from the opposite side of the leaving group. If the alkyl halide at the alpha carbon is a tertiary, well then we know the reaction mechanism will be Sn1. This is because the alpha carbon is too sterically hindered for the nucleophile to attack directly. The leaving group has to leave first. Where we have to consider other things is when we have a secondary alkyl halide. In the case of a secondary alkyl halide, you need to look at what sort of nucleophile you have. If your nucleophile is a strong nucleophile, well then the reaction mechanism that we would expect would be an Sn2. It's the idea that the alpha carbon is not so sterically hindered that the nucleophile can still attack. And if the nucleophile is strong, it's not going to wait for the leaving group to leave. Therefore, the nucleophile will attack in a single step and knock out the leaving group. If our nucleophile is weak, well then we would expect to have an Sn1 reaction. And the idea here is that the leaving group will leave first before the nucleophile attacks. The nucleophile is weak. It has no tendency to really attack. The leaving group can leave because the secondary alpha carbon will be stable enough as a carbocation when that leaving group leaves. So those are the sorts of decisions that we need to make. Now, in our particular case here, I hope you can see that we have a secondary alkyl halide, and this is a strong nucleophile. The only criteria to decide whether or not a nucleophile is strong or weak in terms of our course is whether or not the nucleophile has a charge. And so in terms of strong, negative charge. In terms of weak, it will be no charge or neutral. So we can see clearly our methyl sulfide group here has a negative charge, strong. We're going to expect an Sn2 mechanism. Now, in terms of writing the Sn2 mechanism, I strongly encourage you to write your nucleophile on the opposite side of the leaving group. We will show the attack of that nucleophile with the lone pair of electrons at the alpha carbon and simultaneously the leaving group leaving. This happens in one concerted step. The reason why this mechanism is called an Sn2 mechanism is because the order of the reaction is 2, or the molecularity is 2. Two things are involved in that one rate-determining step. Now, we will usually draw the activated complex at the transition state. The way to draw this is to show, for instance, the leaving group leaving, to show the nucleophile coming in, making, in a sense, a new bond to the alpha carbon, to show that there's been kind of a shift, if you will. We have, in a sense, a trigonal planar orientation about the alpha carbon. Now note, I have drawn in the extra bond to the hydrogen that is understood to be present. It's easier to see the trigonal planar orientation. Now I'll also draw the rest of my ring structure here, but its exact orientation doesn't really matter. It's important to show the trigonal planar orientation about that alpha carbon. The bromide is developing a negative charge, if you will. And the sulfur coming in is, in a sense, losing its negative charge. We'll only put it as delta negative. We usually put brackets around this, and we use this double dagger to indicate that this is the transition state, the highest energy state in this reaction. In terms of drawing the product, remember that there's an inversion of configuration. The CH3S group has come in and is now making a bond to the alpha carbon. I'm going to draw my other bonds in the plane as such, and then I've got the rest of this ring. And then I'm going to show this methyl group still coming out at us, but now oriented towards the right. And I will put also the hydrogen in here, although it's not absolutely necessary to do this. Essentially, these are all the components of the Sn2 reaction. The bottom structure, you can see the conditions are a little different. If we take a look at our alpha carbon, we can see that it's a tertiary alkyl halide. We know that with a tertiary alkyl halide, even though I have a strong nucleophile, there's too much steric hindrance about the alpha carbon, and therefore this reaction will precede Sn1. The first step in an Sn1 reaction is the leaving group simply leaves. We do not draw the activated complex of the transition state for an Sn1 reaction, but rather we draw the intermediate. The intermediate involves a carbocation, and that carbocation is trigonoplanar. We usually view the trigonoplanar carbocation from a sideways point of view. So here is my methyl group still coming out at me, but I'm looking at it, as I say, from the side point of view. Here's my other group going back. This has a positive charge, and then I'll draw the rest of my ring structure. The leaving group has left, and so I can include its structure here. So that's my bromide. Now, it is at this stage that the nucleophile plays a role. I can show the attack of the nucleophile occurring from either side, and therefore, actually, there are two possible products. In terms of one of the products, let's say the attack from the opposite side of the leaving group, I'll have my CH3S making a bond to the alpha carbon. And then here's the rest of the ring structure. My methyl group will be inverted, still coming out at me, but inverted towards the right-hand side. And then I've got my CH2, CH3. In terms of the other product, it actually looked pretty similar to the original reactant, except that the bromine will now be replaced with the SCH3. We have the CH2, CH3 going back. We have our methyl group coming out at us. And then, of course, the ring structure. Small details like making sure that we pay attention to the carbocation of our intermediate, showing the correct orientations of our bonds or about the alpha carbon will be important. And then, of course, making sure that we choose the correct mechanism. I hope this short video has helped you review thinking about nucleophilic substitution reactions.